Hi, I'm Athena Hansen-Ahern, conference producer at Technology Networks, and I'm here to introduce our next talk, Digital Lab, the Next Generation. I'm pleased to welcome Alexei Lapkin and Markus Kraft. Professor Alexei Lapkin received his master's in biochemistry from Novosibirsk State University in West Siberia. He pursued his doctoral research in chemical engineering at the University of Bath and subsequently started his independent research as lecturer, senior lecturer, and reader. In 2013, he was appointed as Professor of Sustainable Reaction Engineering at the University of Cambridge. His research group in Cambridge is focused on developing cleaner manufacturing processes within the chemical and chemistry using industries. Professor Markus Kraft is a Fellow of Churchill College and Professor in the Department of Chemical Engineering and Biotechnology, University of Cambridge. He is the Director of the Cambridge Centre for Advanced Research and Education in Singapore, the University of Cambridge's first overseas research centre, which is based at CREATE. He has a strong interest in the area of computational modelling and optimization, targeted towards developing carbon abatement and emissions reductions technologies for the automotive, power, and chemical industries. A warm welcome to you both. Following the presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. You can also use this feature to connect with attendees and discuss the talk. So feel free to take advantage of the chat system by introducing yourself and sharing your thoughts during this presentation. If you experience any technical difficulties during the presentation, please request help using the technical help icon in the menu on the left-hand side of the player. Without further ado, I'll hand over to Alexei to begin the first portion of the presentation.
Thank you very much. In the first part of the talk, we will discuss how machine learning and robotics can improve biochemical processes. To start with, let's discuss some of the higher level issues. Why do we want digitalization? What does digitalization allow us to do in the chemical sector? When we talk about the high level targets of sustainability, of developing circular economy, promoting responsible consumption, we really are struggling to make sense of those big targets if we don't consider the entire system of chemical manufacturing, from raw materials throughout the value chain into the use and end of use of the products. In order to do that, you need to make sure that the data through the entire value chain, including all of the players, is available for decision-making tools. Those decision-making tools will have to be based on ML and AI, because otherwise you can't handle that level of complexity, that level of information. The details of this paradigm change we've written up in a position paper where the reference is here, together with UNEP and industry leaders. We really think that without AI, we wouldn't be able to work on these type of challenges. A little bit earlier, the group of my colleagues have shown that if you do create such an infrastructure and you connect physical domain with a cyber domain and allow artificial intelligence algorithms to work with the data, you can get significant gains in addition to the proposed, let's say, carbon reduction technologies to achieve the sustainability objectives. Today in the chemical R&D, the digital toolbox is already fairly well developed. On this slide, everything with a tick is something which you can already do. Everything which is in the open box is what is currently state of the art, what is under development, and rapidly there are additions of the new algorithms and new tools in these sectors. So first, let me introduce some of the challenges and some of the topics within this field, and then I will demonstrate how this would work. We start with chemical knowledge. We really need to be able to translate molecules and reactions and procedures into the language which is understood by machines. First of all, for predictions, and then later for the execution. In predictions, here I've highlighted a number of pioneering papers which are already a few years earlier, but these are the papers which propose the early methods on how to convert molecules into machine learning readable formats. This includes molecular transforms, molecular graphs, using descriptors to develop neural networks, featurizing the molecules and so on. The other aspect of the digital chemical toolbox is, of course, automation. And the lab automation is really important and becoming very important in this field. First of all, it allows to avoid routine manual operations, increases the throughput. The robots don't sleep. You can run lab 24 hours a day. It increases the equipment utilization and allows to generate a lot more data to also create the data sets for machine learning. There are a variety of systems which are already proposed. Some of them are bespoke, like this picture here of the system from MIT. There are systems based on batch operations, which are proposed as either at the reasonably large scale or at a very, very small scale for creating libraries of reagents, or keeping libraries of reagents, creating compounds for screening, elaborating the fragments for discovery and automating the process studies. And this same can be done for large molecules. Actually in biologics, this is much more advanced. The cell culture type research has been automated before the chemistry. And this is where many of the techniques are currently actually being shifted from biology into chemistry and adapted for harder operating conditions of many chemical syntheses. When we go into the full system, when we have an experiment and data and hypothesis, we then have to somehow put everything together in the toolbox. And there are quite a few important blocks. So here I've shown what do you need to have. We need to understand what experimental data we have observed. So we need to understand the observations and label them somehow. For this, we need some form of data ontology to be able to figure out what is what coming out from our measurements. That needs to be then inserted into the data which we have for this particular chemistry we're interested in. And the data comes from different sources in different formats. It includes pretty much everything from molecular properties, atomic properties, quantum chemistry, mechanisms, thermodynamics, descriptors, environmental and toxicology data. All of this is the different types of data, which means that we need to be able to work with all of these different data streams. For this, we kind of have another type of ontology, is making sure that this data makes chemical sense, to understand what are the relationships between all of these elements, so that we can convert this into knowledge to be able to generate hypotheses. So we need these mechanisms of automated hypothesis generation, how to generate kinetic models, how to generate properties, how to generate bioactivity models based on the data we have, accumulation of both experimental and library data. And once these hypotheses are generated using AI and ML algorithms, then you want to turn that hypothesis into an experiment. So which machine do you have? Where it is it available? Can it run? How to turn the procedure, which is encoded as I want these conditions to be tested by an algorithm, into the actual experimental protocol that that specific machine can run. And only then the whole thing can actually operate. There are a number of steps here. And the first one, which I'll show you, is how do you deal with the data? And then how do you prepare some of the information for the hypothesis? And then we'll look at how we can run the whole thing in the current lab automated tools. So for developing robust chemical transformations, when some chemists have developed the new procedures, everybody is excited by the possibility of this transformation, but it's actually very difficult to reproduce and really difficult to scale up. In order to make such a transformation an industrial practice, you need to make it robust. So it works under a variety of conditions with different reagents and so on. And in order to do that, you really need to combine a lot of data, and you need to generate a lot more data than the initial discovery. So we've come up with, this was the work of PhD student Perman, he's just graduated. We've developed this workflow when there are effectively two closed loops which operate simultaneously, whereas one is the loop which is a learning loop. It allows to combine the data you generate from experiments with interpretation of the molecules and the reactions in terms of descriptors, and then developing different kinds of features for predictive models and testing whether those models are actually working in the experiments, and repeating this multiple times until you get your target. The second loop is the experimental closed loop optimization, when you have an automated reaction kit and you are collecting new data. You're using the hypothesis generated in the first loop to then generate new data, experimental, added to the data set, and repeat that learning. We've looked at what are the current tools which exist for this process, and already there's a lot of existing tools which could be put into that framework, starting from different kinds of data, then what is a way of generating descriptors, whether through like thermodynamics, through density functional theory, different kinds of fingerprints and so on, then pre-treating this data, assembling the early models, effectively classifying to reduce the dimensionality of the feature space. There are various algorithms to do that. Then how do you run the optimization? How do you develop the initial hypothesis, and so on and so on. So this is a kind of workflow which is possible for the knowledge-based design of experiments, combining both data science, chemical knowledge, different kinds of algorithms, and automated laboratories. When it comes to automated laboratories, for process development, there is quite a lot of work, and I've again listed a number of reviews which are known in the literature, which cover this topic of how to combine experiments with hypothesis generation and with data. My favorite one is the last one from Eli Lilly from 2019. This is really very, very nice review. In our own work, we use commercial hardware which we connect into automated systems. This allows us to have very good control of the reaction conditions. It allows us to create the reactions, so we can choose catalysts, solvents, reagents for specific reactions we want to run. We run those reactions in the smallest possible volumes of plugs so that we don't waste reagents too much. We analyze typically by HPLC. We can also add MS if necessary. And at the bottom of this table, there is a benchtop NMR, well, floor top NMR, which can be replaced, which can replace the HPLC here. When we do this, we typically run this as a Bayesian optimization. We use an algorithm called TSEMA, and this work is described in this paper in Chemistry Methods. When you first run the simple with so-called Latin hypercube, when you explore in the chemical space, you're trying to figure out what is the response of chemistry once you've done that. So these are the gray circles. Then the optimization starts, and optimization already has a model of the space, and it tries to find the optimal solutions. In this case, it optimizes against minimizing cost and maximizing yield. So it has two objectives at the same time. So it gives a Pareto set of solutions, which is this blue line-ish. And of course, the best solutions are somewhere with the highest yield and the lowest possible cost. So this kind of experiments were done by the machine which I've just shown, with the researchers only being there just to feed the system. When it's run out of sample or of the feed solutions, it will send an email and say, please feed me, and that works. When you don't have an automation, it's possible to do this still, but of course we want to have full automation. The challenge is that there are some work streams which are still very difficult to automate. So in the recent paper, we've shown that you can do the same kind of optimization doing experiments manually, but this really is hard work. It takes a lot of effort. So the challenge for the future is to really automate as many as possible different types of reactor technologies, so that these really routine operations could be done fully automatically. In this case, One of the challenges is to use micropacked beds. They're tricky to operate. If you operate them automatically, you really have to have very, very careful experiment. The other one was a kind of mini scale batch for which the experiments, the equipment is quite expensive and it wasn't available to our lab. So the researchers have done this manually, and you can see how many data points they have collected. So this is a lot of work. It's weeks and weeks and weeks of work. And I would really encourage the vendors to develop new machines for automating this kind of experiments so that this is no longer required to run this manually. Now, the limitations of the standalone system like this one, we now have two of those, we have two labs and one in each lab, is that they're not really fully automated. We would like to link them to the electronic lab notebooks. We would like to link the two systems between our labs so that we can use both of them in the same experiments. They are not so easy to run different tasks. So if change chemistry, you have to change quite a lot on the system, and they're not really connected with any other tools which you may have, like an inventory, scheduling, lab sort of lab data, and so on. So in order to do that, we have come up with an approach which is based on a dynamic knowledge graph. So dynamic knowledge graph would allow us to connect the two systems and connect effectively everything in our labs. What we're currently developing in the center, so I'm sitting with, this is the advertising at the back, IDMT Center in Cambridge, which hosts the high throughput lab, the robotics lab, where we are gradually digitizing, creating digital twins of all of the lab equipment and putting them on the knowledge graph so that everything can be accessed and operated by researchers pretty much from anywhere in the world. So this concludes my part, and I would like to invite Markus Kraft to introduce the knowledge graphs.
So thank you, Alexei. So let me explain how we can use dynamic knowledge graphs to improve laboratory automation. The first thing I want to say is what is a dynamic knowledge graph, and we have chosen the word avatar as its name. So there are a few key statements that describe it. So the word avatar is a dynamic knowledge graph. It combines data and concepts and computational software agents. So it's not just a data platform. The agents are autonomous within the knowledge graph. You now see here a green area and a red area. And the green area you can think of as being your hard disk, and the red area you can think of a memory. And each dot here represents an internet address. So imagine your hard disks being the sum of all the hard disks that are connected to the internet, and the red area is the sum of all memory connected to the internet. So we describe data not just in form of a data point, but also in forms of ontologies. We use triples. This is a specific way of representing concepts and data in a specific format called our format. It's part of semantic web. These are well-established internet formats which we use, and we not only represent the concept and the data, but also the software we use to modify it. So this whole thing builds an enormous graph that stretches over the internet, basically like a web. And the red level shows the software, which we call agents, that modify this graph and determine the input and the output. So we will see this in a minute. So the key point here is everything is connected. That's a key important statement. Right, and the beauty about this concept is, about this architecture, it's unambiguous because everything has its own internet address. It's connected, it's scalable, it's accessible, it's multi-domain interoperable because of the different concepts being part of the system, and it is evolving in time. So this gives you a very, very general framework to represent knowledge and data and being able to modify it as you go along. So what are our objectives? First of all, we want to represent any aspect of the world in a digital world that we call base world. We form a general purpose and all-encompassing data storage and modeling framework. We contain concepts and data that describe the real world that are operated on by computational agents. And we allow the creation of scenarios or parallel worlds connected to the base world in real time. So these are our objectives, and how do we now translate this into lab automation? And this is what I want to show you in the next few minutes. And Alexei already described our lab robot and how you can use machine learning to operate it. And so what you now see here is the real world in gray, with the lab in Cambridge on the one hand, and the lab in Singapore on the other hand. You then see also how this laboratory is connected to the individual assets. So each of these symbols represent basically an instance in the ontology. We use different concepts to describe this. For example, we use ontospecies to represent the chemical species, ontoreaction to represent the chemical reactions that are going on, ontolab to represent the hardware, like the HPLC or the reactor, and onto DOE, that is the ontology that helps us formulate hypotheses. And these concepts are then used by the agents that you see up here in order to operate the experiment, similar to what you've just seen in the slides before. But now we go one step further. You know, this reactor does not only exist in terms of chemical space, it also exists in terms of the laboratory, the actual piece of equipment that is on a bench and that has an asset number. And here you see a building information model, a representation of our robot. So that information too is part of the World Avatar knowledge graph in this case. Right, so as you now have seen, we managed to get the lab robot into the knowledge graph. So, but more general, we can go from chemistry, from the assets to laboratory, to building, to cities, and even bigger. And you know, objects have a spatial dimension, what I've just shown in the building information model, but they have a geometry associated and the function, in this case, the robot. And for all these aspects, you will find different ontologies that are all important in a way in the World Avatar. Ontology represents a knowledge model of a specific domain. And you see, for example, geographic information system ontology stretches from cities down to rooms in a building. And then you have the building information model that stretches down to assets and so on. And what I'm trying to do in the rest of this talk, I'll show you a quick example of different use cases. So I'll talk quickly about building management system, inventory management, reordering chemical and automated experiments. That is what I've just described earlier. So just to give you an idea where our Singapore lab is, let's fly in. Okay, and now you see our laboratory. You see the fume cupboards that are connected to building management system. You will see also our representation of the robot that Alexei mentioned in our laboratory in Singapore. You see now our explosive precursor cabinet that contains these different bottles of precursors. And last but not least, you see our another fume cupboard, but now our fridge. And this fridge is connected to Arduino board, which I will just demonstrate, where I demonstrate the ability to control Right. So, okay, let's just go through the different use cases. As I said, we have the connectivity to the building management system, the explosive precursors, the robot, and the HPLC in asset management. So let's have a look. Okay, this is our explosive precursor storage cabinet. And so we have a system of agents, and I don't want to go into these agents in detail, but I want to explain to you how it roughly works. So you see our explosive precursor cabinet. You see 3 bottles. So now somebody comes and removes 1 bottle. Okay, so what happens? Okay, so this is the state of the explosive precursor cabinet. It sees, oh, bottle 2 status is out. And then behind the scenes, the knowledge graph checks what is the inventory. And if it takes too much time, it would then send an email to the lab manager and says, whoever removed this bottle 2 didn't turn it back. So bottle 2 of the explosive precursors has been removed from the cabinet for more than 3 hours. And the chemical in it was sodium perchlorate. And just for information, there's a hazards and warnings. So it may cause fire, explosion, strong oxidizer, harmful if swallowed. Okay, now let's hope nobody swallowed this material and it just turns out that the bottle is empty and it wasn't reported. This is a way of increasing the security level within our lab. Okay, the second aspect is a very small control example. So many of you may know what an Arduino board is sort of a small mini computer that you can use to control all sorts of things. In this case, there's a temperature sensor in it and a fan. And the Arduino board is actually used to monitor this, the current quality that goes into the lab and see whether the overall smart city energy regulation has, for example, a different phase angle that would maybe have impact on some of our piece of equipment. But what we want to do is we want to avoid the Arduino board to get too hot. And for that reason, we have instantiated the Arduino board in the knowledge graph. We record the temperature. We look at the status of the fan, and we use 2 different cloud platforms to connect to it before we instantiate it. We then, if the temperature sensor gets too hot, agent 3 would then communicate with the fan and switch it on or off. Right, so this is an example how the knowledge graph can actually operate on the real world. And finally, we're talking about the building management system that is now it's a professional Schneider building management system that not only runs the lab, but the whole building. And we have instantiated it. And the classical example is the airflow sensor within a fume hood. And so this is the way it is instantiated in our model. You see, okay, the manufacturer name, the model name, and you see the current airflow. And what you can also see is the percentage of opening of the fume hood. And of course, many researchers forget to close this before they go home. So we can send email to the lab manager that can then close it, and with that, save some energy. So that sort of completes the overall tour of the digital lab. And let's have a quick moment to think about what we have done. So we have represented aspects that are static to aspects that are very dynamic. So from automated design of experiment to asset and device management. For each of these points that you see here in this list, you will find there is software that already deals with it. So for example, the asset and device management, maintenance and calibration, chemical inventory management, that is part of ERP software, enterprise resource planning. Then you have chemical inventory management, lab notebook management. You would find that in electronic lab book, workflow and project management, sample and patient management. So that is lab information management system and automated analysis of experiment, automated execution of experiments, an automated design that you would find this in the chromatography system or scientific data managed system and lab execution system. Now, the beauty about the work I've just shown you within the World Avatar is that you can incorporate all of this in one system. And this is the key advantage of that system. Right. And that brings me to creating digital scientists. So we have a digital building manager, a digital lab manager, and a digital researcher. And they have different tasks. So for example, the building manager provides a stable environmental condition, management of repairs, infrastructure budgeting. The digital lab manager, safety, stock taking, asset management, and the digital researcher, design of experiments, measurements, modeling and simulation, and data analysis. So, and you can see in the second level in the representation, so the building management deals mainly with the infrastructure and the lab manager with the devices and the assets, whereas the digital researcher would deal with chemistry. But of course, everything is connected. And this is shown by these lines that go from one digital researcher to a digital lab manager and potentially also the building manager. And if you now go back to our use case examples and you think of the people that we have represented. So, for example, the HPLC may need the temperature of the building, so it needs to go to the infrastructure and queries this. And for example, we use chemicals that require some special safety treatment, and for that, the digital researcher would consult with the lab manager, and at the same time, the lab manager wants to have information from the building management system, and this is how that is connected. So the World Avatar and the Dynamic Knowledge Graph offers an instrument to connect all these different tasks in one system, and we will grow this together, and in particular also incorporating more chemical knowledge and hopefully make new exciting discoveries. And that brings me to the conclusion slide. Let me just go through what you have seen today. So first of all, we argue that a self-optimizing lab system can improve key features of chemical reactions such as yield and cost by combining programmable chemical handlers, machine learning, reaction optimization algorithms, and online analytical techniques. So integrating this work into the World Avatar absorbs the heterogeneous data and services, achieving interoperability and hardware independence. The World Avatar creates scalability and collaboration across different platforms simultaneously. We can also use chemical knowledge from first principles while accessing environmental information. And with this, I would like to thank my collaborator, Alexei, and everyone who organized this seminar, and I would like to invite the audience for questions. Thank you.
Thank you so very much, Alexei and Markus. As with all the talks, we're likely going to have lots of questions from the audience, and I can see that we've received some questions already. So I will move straight into the Q&A session now. Your first question, how is this knowledge graph approach different from a digital twin?
The knowledge graph, in a way, I always explain it, it's sort of the mother of all digital twins. It's the digital twin of digital twins because it allows sort of to host a whole variety of digital twins, if that makes sense. So just like we have a digital twin of the fume cupboard and a digital twin of the lab robot and a digital twin of the building management system. So it incorporates these things and connects them.
Amazing. Another question for you both. How will machine learning improve the interoperability of models?
Right. So how to answer this question? Now, in the first instance, I told you that the knowledge graph is a directed graph consisting of internet links with in a format that is well established called OWL. it has the ability to use description logic to infer statements. Now, this representation, although very rich and powerful, can be quite slow. So you could use machine learning to speed up the connectivity of the different entities and therefore increase interoperability by speed and get the machine learning to the point that it can infer knowledge. So we not just do machine learning of data, but actually do machine learning of a knowledge representation. Does that, I hope this answers the question.
Certainly. Amazing. Thank you so much. Another question for you. What challenges must you overcome to be fully functional?
Markus or me? I'm happy to answer this.
Good.
So in order to be fully functional in the lab, well, first of all, you need to have qualified people who are enthusiasts. You need to have a group which combines the skills of automation, coding, software development, as well as chemistry and chemical process development. That's one of the biggest challenges today is actually having all of the right skills in one place. The rest of it can be expensive or can be relatively cheap. The software architecture doesn't have to cost you a mile. The equipment, pretty much everything can be automated by Arduinos, very, very cheap, or can be done with commercial, fairly expensive equipment. So it depends whether the labs are on a tight budget, Arduinos and relatively low-cost lab instruments which have the drivers to be automated are all that you need. But I would again come back to the start of the answer. You really need to have a skilled team. That's is the most important thing.
Amazing stuff. One last question for you then. What are the next steps?
Well, the next steps for us is to try to demonstrate the entire environment. I anticipate that there will be a benefit of scale once the individual instruments are connected. There is an environment in which there is data, experiments, and machine learning algorithms. I think it will open the creativity and it will allow a lot more things to be done, which I probably don't even anticipate today. There is a number of things I would like to do, but those are probably quite boring by what will come once that such an environment is actually in place. Markus, do you have anything to add?
Well, I'm enthusiastic about the future as always, right? One thing I would like to do is emphasize what you've said earlier. We are always looking for good talent. And if you feel that you like what you see today and you want to be part of our team, I can only encourage you to apply to open positions in Alexei's and my group. But so that could be the your personal future that develops into unexpected areas. But I personally see this automation. Now we have just made the first steps. We will be able to retrieve knowledge using machine learning, combine the two things together, and potential outcomes could be better catalysts, new medicines, and we will have to see how we can develop our infrastructure and algorithms further to step exactly in this direction. So I'm very excited and can't wait what's happening.
Fantastic stuff. Thank you so very much, Alexei and Markus. Unfortunately, that's all the time that we have for today. Any questions that we didn't have time to get to will be sent to the speaker after the event. And as with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. That just leaves me to say thanks again, Alexei and Markus, and we'll be back soon with the next talk.
Okay, thank you. Bye-bye.